want to welcome everybody to the first colloquium of winter quarter. And we're really fortunate to have as our guest speaker a former student, Jeff Bigham, who's now an assistant professor at the University of Rochester. He's actually quite famous already for such a young person. He's won many awards, including the Andrew Mellon Foundation Award for Technology Collaboration, the Imagine Cup, Microsoft Imagine Cup Award, and the TR 35 Innovators Under 35 Award. And I'm sure there's going to be more downstream. And it was a great pleasure to work with him myself personally for, 4 years or so. And I hope we're going to work in the future. But today, he's going to talk about a very exciting topic, heads in the clouds, and using technology in the cloud to solve accessibility problems. Jeff?
Well, thank you, Richard, for the very nice introduction, and thank you for inviting me here, and thank all of you for coming to see me speak. It's kind of wild being back and recognizing maybe a quarter of the people in the audience. So Richard mentioned a lot of the stuff that I did while I was here, but he didn't mention, and I felt like it would be just too bad if I didn't mention one of the other activities I was involved with when I was here, and that is in historical reenactments of various department events. Some people recognize this. This was a reenactment that Yao Nakwa and I did of the epic battle between Department Chair Hank Levy and Yao Nakwa, graduate student, when Hank had the idea that he was going to steal the superpowers from the faculty in order to take over the world. So here's a short clip of that. All right, so I figured a talk that started off with that amazing video couldn't go badly. But the real topic of my talk is, as Richard said, heads in the cloud and how we can use the cloud, services based in the cloud, and human computation to address some of the remaining problems with assistive technology. And so the context for all this is that over the past few decades, there's been a lot of just wonderful access technologies that have been developed. Things like screen readers that convert the visual information on a computer to audio so that a blind person can use it. Things like speech recognition that can transcribe spoken words for deaf and hard of hearing people. Things like wayfinding systems that can help people with cognitive impairments stay on track. But like a lot of the intelligent user interfaces out there, these systems still have limitations. And when they fail, people can be very discouraged in using them. And so even if they only fail every once in a while, the potential of these really cool technologies is greatly reduced because people can't rely on them. So in this talk, I'm going to be speaking about how we compare the rich history of innovation in assistive technology with the advantages of the cloud, in particular two things. One, the ability to deliver services wherever people are as long as they have some kind of internet-connected device, and the ability to pair people with other people. So essentially, to back up fragile automatic assistive technologies with people out on the web who can help solve problems that need solved. The context for a lot of this started while I was here at the UW. Where I worked on a project called Web Anywhere. The idea of Web Anywhere was pretty simple. We were going to package, or we did package up an assistive technology called a screen reader into a web application that blind people could use from any computer that they happen to have access to. Even lock down public terminals on which users would not normally be able to install or run new software. And so this is pretty important. It seems like it might not be, but it turns out to be very important because of things like the cost of a screen reader. So here's a little scale that shows a screen reader at $1,000 and the computer that you would use to run it at only 2.5 times less that, so $400 for a brand new computer from Dell. And so that means that if you go to the hotel business center, or you go to a library, or you go to your friend's house and try to use their laptop, it's very unlikely to have the assistive technology that you might need to use that computer. And so by building this into a web application, we could deliver that to any computer that was there. And what's kind of neat now that we've seen since when we first started developing these, this type of a system, this mobile smartphones with rich internet browsers have become much more popular. And I can actually pull up Web Anywhere on my Android phone. I can pull it up on my iPhone. And because it's built into the web, it can run on all these different devices. So just as a quick demonstration of what this looked like, I'll play just a short video, and I'll probably cut it off early since many of the people here have seen this. But this is Web Anywhere running inside the browser.
Web Anywhere has loaded. 3 headings, 1 link. Welcome to Web Anywhere. Heading 1, Web Anywhere Alpha Release. Web Anywhere has been initialized and is now ready to use. Link. Web Anywhere is a non-visual interface to the web that requires no new software to be downloaded or installed. It works right in the browser, which means you can access it from any computer, even locked down public computer terminals. Location field text area. LMOC page has loaded. 0 heading 9 links. Gmail, email from Google. Text area email. SCRENR.
All right, so I'm going to stop it there. I'm not going to go into all the details about how this works or the technical challenges that we had to solve to make this work. But basically, it's just running as a JavaScript program in the browser, which makes it compatible with almost any browser that you would have on any device that you'd have. And what we did with this is we actually released it, and a lot of people started using it, which is pretty neat. But what we found was that not all of those people were actually blind, as we had built this tool for people who were blind. We expected that, but instead, a lot of the people that were using this were actually using it to support reading. And so this was kind of odd to us because not only was this a web application that I developed as part of a PhD dissertation, which means maybe this isn't true of all of your projects, but it means it's a little bit flaky. But also this wasn't targeted at that population. And so there must be something about this availability argument that encourage people or convince people that they'd use this technology that's not exactly targeted at them for something that it's not meant to support. Since that time, we've actually developed extensions to Web Anywhere that are directly aimed at supporting reading. And so I'm going to play a short clip here of a version of Web Anywhere that's built into a web page that's actually going to highlight word by word what's being read so that somebody with a reading difficulty might be able to benefit. You can also learn about giraffes here.
The giraffe, Giraffa camelopardalis, is an African even-toed ungulate mammal, the tallest of all land-living animal species, and the largest ruminant. The giraffe's scientific name, which is similar to its antiquated English name of camelopard, refers to its irregular patches of color on a light background.
Okay, so that was a little bit about giraffes. And what I think we learned from this project, and why I included a few slides here at the beginning about Web Anywhere before I get to the main topics of my talk here, was that we found that availability was really important. It wasn't just that we needed to improve the types of assistive technology and access technology that are available to people, but we needed to make it so it was easier for them to get access to it. And that's what Web Anywhere was really great at, and that's what encouraged people and convinced people that even if this wasn't exactly the right tool, and if it didn't work exactly right all the time, that they could still use it and benefit from it. So one of the things that, since I've graduated and moved to the University of Rochester, we started thinking about is how else might we improve the availability of the services for people with disabilities. And I'm really encouraged by a quote that I'm going to put here on the screen that we got from one of the participants in a survey that we conducted a little over a year ago. The person said, "I get so frustrated when I need sighted help and no one is there." Now, this quote needs to be taken in context. It's not that this person is saying that they need help all the time. That's certainly not the case. But what it's saying is when things break down, when plans break down, when the technology doesn't work as they expect, the way that people recover from that is that they'll ask somebody for assistance. And so we began thinking about how we might be able to build technology that's robust to that type of a situation. And not surprisingly, we're not the first people to think about this. This is a picture of John Braben, who's from the Smith Kettlewell Eye Institute in San Francisco, taken almost 30 years ago. They were developing and continue to develop all kinds of great automatic technology to support people with disabilities, in particular blind individuals. And here, as John tells the story, he thought it would be funny to basically take every one of their projects, put it on one of the employees that works with him, and go out into the street and see what would happen. And so the picture here has this guy has some kind of electronic cane. He's got a big belt around his belly that I think has different tactual sensors on it. He has headphones covering off all of his hearing. So hopefully whatever information he's getting from that is going to compensate for all of the great information you get from the environment. And then all kinds of other stuff that I actually don't know what it does. So what's really neat about this is, this has been going on for 30 years, where people have been developing technology that's supposed to help people recover when existing strategies fail. And a lot of great stuff has come out of this, right? So just as some examples of this, we have optical character recognition, we have color recognizers, we have automatic speech recognition. And these can solve a lot of problems, right? So we can recognize text, convert it to speech. The color recognizers, you might wonder, why is that important? Well, things like coordinating an outfit, that's something you could do with a color recognizer. Unfortunately, despite the promise of this technology, it remains limited in scope of the problems that it can reliably solve, and it still has unacceptable error rates for real situations. So a lot of people, when they think about OCR, think that it's a solved problem. And it is solved if you're talking about black text on a white piece of paper that's scanned at a high resolution with, it's using a normal font. But if you're talking about a blind person who has taken a picture of a street and is trying to get the text of the street sign read to them, it's not a solved problem at all. Even finding the text in that photo is not a solved problem. And on top of all of that, and on top of the limited scope and the high error rates, the technology remains quite expensive, hundreds or thousands of dollars for technology that will often work. And it is actually a big triumph in science and engineering that it works as well as it does, but often has problems. And then even if it worked, because of the limitations of what we can do automatically, this technology isn't always exactly what users would want anyway. And so I'll demonstrate this with a beer menu. So here's a menu from a brewery. And there's a whole lot of text here. So all the things you could possibly get at this brewery. And so now let's just assume that even though there's kind of funky fonts here, and there's different sizes and all of this, let's assume that a generic OCR engine could actually transcribe all of the text on this menu. It's still going to take a while for a blind person to get the information that they really want, because absent all of the great visual cues here, the headings, the other just graphic design elements that help us quickly narrow in on what we want, it's going to take them a long time to answer a question like, what's the cheapest burger? Which, at least that's my usual question when I go. So if you're wondering, the cheapest burger is actually down here, the no frills cheeseburger. And so the question is, how could we help support a user who wants to answer just simple questions like this from a menu, something that visually is pretty easy to tell, but even if the technology, the best technology that we have right now, worked as it's advertised would still be pretty hard to answer. Well, my answer, and a lot of people's answer to this question of what to do when automatic technology fails, is to include humans in the loop. And there's all kinds of great examples of this, and I've just put a few here, which I'll run through just very quickly. Cha-Cha and KGB are these services where you can just text questions to the service, and they'll, through some combination of automatic and human services, send you back an answer, so you can settle that fight you're having in the bar. Remote real-time captioning. There are services where you can pay someone to sit at a computer at their own home, listen in, and caption as you speak. Different, more recent systems like Soylent and Turkit allow you to engage workers on Amazon's Mechanical Turk and actually coordinate groups of workers to all participate in solving a single task. So Soylent helps you do things like, that Kai paper you have that's a little bit too long, what helps you shorten it? Or it actually provides human-powered grammar fixing. Social accessibility is a project out of IBM Japan, where the idea is that if you're a blind person who's browsing the web and you run into a problem, you can actually send that problem out to volunteers out in the cloud somewhere who, after a hopefully small delay, will fix that web page for you. And the next time you visit the web page, that problem won't exist anymore. So maybe it'll add an alternative description to an image or add headings so that you can more easily go through the content of the page. A service called oMobi, which is kind of a spin-off from computer vision researchers at Berkeley, has a mobile application where you can take a picture and get a description of that picture back right on your phone in nearly real time. And one that I think is particularly inspiring and maybe troubling, but we'll say inspiring, is Salona, which is a service that helps blind people solve CAPTCHAs. So if you might imagine, CAPTCHAs are not particularly easy to solve if you can't see them. And so what started out as one guy who recognized this problem has grown into several people who all, if you're allowed access to the system, will solve CAPTCHAs for you very quickly. And so the idea of falling back to humans is already pretty commonplace in the accessibility world. And to illustrate this farther, and again going back to the Smith Kettlewell Institute, there's some descriptions there. I want to talk just briefly about the system that they had. This is back in the early 1990s. And this idea of the remote access to visual material, this is a sketch of a service designed, implemented, and actually run for a short time by the Smith Kettlewell Eye Institute in the early 90s. They'll let a blind person fax a picture of something that they wanted transcribed for them, and then receive a description of that item via the phone. And so, I like this picture for a lot of reasons. First of all, I think it actually predicted a lot of the work that's happening now on human computation, where you engage these remote workers to help do work for you. But I also like it because if you notice, the remote worker there is herself in a wheelchair. And so I think that's a nice addition. Here's a picture of a guy actually using this. So he's got a fax machine. He's got like an envelope there that he has on the fax machine. He's getting information about who sent the envelope. So we looked at ideas like this, and we thought, well, if we go back to this early picture I showed you, one difference between now and then is that then you had to have all of this stuff strapped to you to have all of these great sensors onto the world. Now I have a lot of sensors right here in my phone. And so that's one trend that's been happening. And not only that, but it's actually connected to a network. And there's all of these great services out there that allow you to engage humans to help interpret the sensor information. And as we'll see, if we do a little bit of tricks, if we perform a little bit of tricks, we can actually get the answers back in the interpretation of that sensor data in nearly real time. So in particular, we built a mobile application that we call VizWiz. And this is a mobile application that lets blind people take a picture with their iPhone, speak a question into their phone, and then get answers back from real people in hopefully just a few seconds or under 30 seconds. So let's see. I'm going to show a quick video before I describe how this works of Yasmina here, who is a blind student from Rochester, who's going to be using VizWiz to find out who sent her this letter.
Double tap again to both start and stop asking a question.
Can you tell me from whom this letter is from?
Please wait while your question is sent. Question sent. Awaiting a response.
Yasmina's question gets sent off to remote workers on the web who will look at the photo she took and attempt to answer her question.
Okay, so this is where the realistic latency in this video comes to play.
The answer is Sam White of the University of Rochester.
All right.
Okay, so what I think is just a few things I wanted to point out here. First, you might have noticed that Yasmina's iPhone was talking to her. So this is from a program that's built into all the iPhones now called VoiceOver, which speaks the interface to the iPhone. And Sean Kane, Jake Walbrock, and I actually did some early work on showing that if you design the interface right, it might not be intuitive, but a touchscreen or touch-sensitive surface that talks can actually be more usable and more preferred by blind people. The other thing I think is interesting here is because we're using people, it didn't matter that Yasmina has an accent, right? So if we were trying to convert this to text and only showed people the text, then this would be unlikely to work. I know a lot of people, especially, this is all the rage in computer science now, so many people are familiar with Mechanical Turk. But just briefly, this version of VizWiz that I just showed uses a service called Amazon's Mechanical Turk, which is essentially a marketplace where you can pay small amounts of money to have real humans do small jobs for you. Mechanical Turk is a pretty great platform to prototype technology like this because there's a lot of people online at all times, so you don't have to worry about finding these people to answer questions at 2 in the morning. They're actually already there. And I'll speak later about how we've extended VizWiz to use other sources of human computation, such as your friends on Facebook or your personal contacts with text messages, and also talk a little bit about the interesting problems that those sources of human answers can inspire. But a little bit more about how this works. Okay, so this is maybe the necessary systems diagram. And so these are the remote services that make VizWiz possible. So we have a web server here that stores questions as they are asked and performs speech recognition on the questions. As you might guess, and clearly with the example I showed, speech recognition often doesn't work. And so the worker interface also plays the audio of the original question. So this is actually the web page that a Mechanical Turk worker would see. So you see the picture, they have a big box here where they can type the answer. If the speech recognition works, or even if it doesn't, it's shown here, but they still hear the question playing. So when the user asks their question, it's sent to the server where they can speak when they speak their question, and then we try to recognize the speech. When the answers come back, then they are automatically sent to the phone. We actually end up recruiting more workers than we actually need, just because there's a high variability in the response time from the different workers. And so by recruiting more workers, we can actually get our average latency down. To further speed this up, we actually end up pre-recruiting workers, and we signal to the system here called Quick Turkit to start recruiting workers when the user starts messing around with the phone. So when they start taking their picture, before they've sent it, before they've asked their question, we already send a ping off to the server that says, hey, there's probably a question coming. You might want to recruit some workers. We deployed VizWiz to 11 blind iPhone users over a period of about a week, and they asked all sorts of interesting questions. Some of these mapped to what existing automatic technology either does or is trying to do. So for instance, somebody asked, what color is this pillow? What denomination is this bill? Others didn't. So here's a question that somebody asked. It says, do you see any picnic tables across this parking lot? So they presumably had arrived at a park, were looking for someplace to sit, and they wanted to get a sense of what was around them. And this is actually a very common desire of technology from blind people, is to, when you're in an unfamiliar place, to get a sense of the space. For some of the questions, I actually really don't know how workers were able to answer it. So for instance, this question says, can you please tell me what this can is? And the picture is of the back of the can, and it's really hard to tell. So it is actually, the answers are chickpeas, beans, and Goya beans. And that ends up being right. You can kind of see, if you really look carefully, you can see there's like a little, I think the last part of chickpeas or something on there. And so you can make a good guess. But I think this illustrates two things. The first is, it's really good that we had humans doing this and weren't trying to do this automatically, because I think it would be very unlikely to work. But the other is that, and we'll get to this later, we're having blind people who cannot see the viewfinder take pictures. And so this is something that we should expect, and we'll see more of that. And we have to know to make our technology robust to all sorts of different pictures. Across all the questions that users asked, they got a correct answer in just over 2 minutes. And with the payment scheme that we had, they got a little over 3 answers, and for a total cost of about 7 cents. So the answers cost between 1 and 2 cents. And just to add redundancy, so that if there was a worker who gave an incorrect answer, which we actually didn't see very often, you would have that redundant answer to make sure that you got a right one. We had workers answer, or more than one worker answer each question. So we dug into the data a little bit, and we found that not all questions or answers are created equally. For instance, if the question wasn't answerable, so this is most often because the question couldn't be answered from the picture that was sent in, then it took a lot longer for Turkers to respond. Now, this is presumably because they didn't know how to respond, and they didn't want to risk getting their job rejected just because they guessed at a question that they couldn't or weren't confident in the answer of. But when speech recognition worked, we got a lot faster answers. And so again, this is presumably because they didn't have to wait for the audio to play, and we didn't have to find a worker who actually had their audio on. And I think the bottom line, though, was that 87% of the time answers were correct, and we didn't actually see any malicious answers. Most often when the answers were incorrect, it was because the person had misinterpreted what they were supposed to do, like they transcribed the audio instead of answering the question, things like that. So one of the things we really tried to do well in this project was get answers back quickly. And so this is a simple, and to understand the ways we went about doing that, this is a very simple diagram of the time breakdown on Mechanical Turk. So when you post a job, you waste some time just recruiting a worker. So you have to waste a little bit of time as your job is there, waiting for someone to find it and actually accept the job. We can increase the frequency of being ready for workers being ready to answer a question by having them do more than one job. So here, these red lines represent the time at which the worker is actually ready to accept a new job. So we have them do in our case, 3 tasks. They're all just the same. We just pull the questions from previously asked questions. And so in this case, if we have 3 tasks for them to do, then the worker is ready at 3 different points. We can also recruit multiple workers who will each have their own times to be recruited and times required to complete the tasks. So that looks something like this, right? So we have a bunch of different workers. They all take different amounts of time to be recruited, and then they all take different amounts of time to actually complete the tasks. What's kind of interesting is that as the number of workers increases, we start having a worker ready for a new job at almost every point. And so this is illustrated by moving those red lines down, and you see that because of the variability in the recruiting times and the task completion times, just the fact that there's a lot of workers, you start having a worker ready to do what you want them to do pretty frequently. I also mentioned that we use another trick to start recruiting workers once the user begins asking or using the application. So once they begin taking a picture, we begin recruiting workers. And so doing this allows us to subtract the time required to take a picture and speak a question from the time to recruit. And if asking the question were to take longer than it takes to actually recruit the worker, then we can effectively erase all of that latency. So when they start taking the picture, we start recruiting the worker. And if we're fortunate enough for this time to be less than the time it takes here, then we don't have to wait for that worker to be recruited. And I'll show you some data here in a second that actually shows that we can't quite remove all of the time, but we can get pretty close. To encompass all of these different strategies, we built this toolkit, Quick Turkit, which is a Turkit script. So Turkit is an abstraction layer on top of Mechanical Turk, built by Greg Little of MIT, that embodies these strategies. It's essentially a big loop that just keeps asking how many workers do we need based on the current conditions, and how many workers do we currently have actively engaged answering questions for us. So if we need more workers, it posts more hits to Mechanical Turk. So hits are the jobs that we post for people to do. And if we have as many workers as we need, it starts removing those hits. We also use a number of just simple SEO tricks. So we'll post more jobs than we need. We'll stagger the jobs. So one of the default views that workers look at is the most recently posted hit. And so we stagger the jobs so we're more likely to be in that list. And we also use multiple titles and multiple prices to try to capture different parts of the market. So the paper actually has a number of really great results that we observed from workers on Mechanical Turk. But here are a few that I think are particularly relevant. First, for our task and our users, the lead time was actually pretty high for them to take a picture and speak a question. We found that on average it took about 78 seconds. And I think that part of this, and most of this, as you see, taking the picture took the most of the time, was actually framing the picture, figuring out, is that really what I want to take, and things like that. And so the lead time of 78 seconds gives us a huge benefit in decreasing the experience latency. So we can take away from that recruiting time about 78 seconds. The average time for a worker to actually complete one of our jobs was just 36 seconds. And so that means that worker who's doing a task every 36 seconds is available every 36 seconds. And so what that allows us to do is have those workers available more often. So you want the workers to complete your jobs quickly. Let's see. So there's our lead time. And this is the time, if you remember, if we do our best where the speech recognition works and everything works out just right, we can actually decrease that wait to pretty low. We decided we were going to pull out all the stops. We made a second version of VizWiz. And in this version, we made a number of improvements. One was that we found, not surprisingly, taking pictures was pretty difficult. So we built in some just basic feedback. So things like blur and darkness detection which can help just eliminate the kind of the obvious errors, right? So especially with the iPhone 3GS, which is the iPhone that was used in this study, the camera was not that great. And so we often find dark photos even in rooms that were lit. We'd also find very blurry photos. And so we just gave them, the user some just simple feedback about whether the picture looked very blurry or very dark. We also used Quick Turkit. Instead of trying to recruit workers on demand, we just used it to keep a steady pool of workers around at all times. And so we were able to just set a goal of maintaining 8 workers at all times. And we could do this pretty cheaply. So it only cost about $4.67 an hour to keep 8 workers around answering questions at all times. And when we did all of this, the end result was that we could get first answer back in less than 30 seconds, in 27 seconds. And if we had speech recognition work, then it was even faster again and down to just 18 seconds. And so this is this is why we think that this is actually reasonable to employ in one of these interactive systems, because even though it's using human computation, it's actually very quick. And you could imagine, and actually we found with some of our other projects, that running computer vision on these devices can actually take a while as well. And so this is kind of competitive, at least right now. We've done a number of extensions to this project. One of those we call AudioWiz. So AudioWiz is essentially analogous to VizWiz, but targeted at deaf and hard of hearing people. The difference here is that we're using audio, so the workers are going to be transcribing audio. How the system works is it's always recording, but most of the time not doing anything with the recording. So it's just keeping a buffer of 30 to 60 seconds. And then if the user decides that something has likely happened, so the example I like to give is you're sitting in an airport, all of a sudden everyone gets up and goes somewhere. What's happened, right? So it's very obvious that something has happened. And what's worse is that if this worked like VizWiz, where you actually had to capture the sensor data at that point, it was too late, right? So the temporal nature of audio means that it's already gone. And so that's why we keep this buffer, so that when everyone gets up, you can then query Mechanical Turk with the last 30 seconds of audio and get a transcription of what's happened, so that you can find out what's happened after the fact. And so this is just a little screenshot of this system running. So the idea is it's recording. You can choose how long ago you think that the event happened, and then it gets sent off to Mechanical Turk. There's a little bit of time waiting for Mechanical Turk to get back to you, and then you get answers like, United Flight 815 has been moved to gate 37, things like that. The interface for Mechanical Turk is pretty simple. We just have the audio playing, and then optionally you can provide some context. So here, where did they say they were meeting? So maybe you're outside of a class, you miss your study group because your interpreter at the end of class had to go. You miss where they said they were going to meet up to study later. And so this type of a system might be able to help you catch that little bit of information. It gets pretty interesting when you start thinking about how we might be able to add in not just human services, but also kind of automatic services. So I mentioned at the beginning of the talk, there's all this great technology that's been developed, like speech recognition and other things like that, that is not being used to its fullest potential just because it has that high error rate and it has kind of that limited scope of problems that it can reliably handle. But if what you're doing is using both human computation and automatic computation, then maybe if we try really hard, we can get the best of both worlds, where the automatic technology works for free and very quickly when it works, and then when it doesn't, you still get the benefit of the technology working because it's backed up by people. And so here's an example of how that can work with AudioWiz. A question I get asked a lot is if the economics of this actually work out, right? And what happens when people stop wanting to do work on Mechanical Turk for a penny? Will that happen? But I think what's interesting is that the economics in assistive technology are such that human computation, even paid human computation, even reasonably paid human computation, might make sense. So here comes what I think is my one equation in this talk. So if we take a really great assistive technology like the KNFB reader, which is a mobile OCR device developed for blind people that allows people to take a picture and get the text spoken back to them. This costs $1,000 just for the software. And if you get the phone that it runs on too, then that's another $500. So let's say here's my $995. I divide that by approximately 5 cents, which is what we can probably get answers back for now on Mechanical Turk. And you could actually ask people 20,000 questions for the same price as just this one access technology. But of course, what does that actually mean from the worker's perspective? Well, I told you that the average time to answer a question for Mechanical Turk workers was 36 seconds. If we figure out what hourly rate that is, it's about 67 cents an hour. Probably not very good, although there is a paper that suggests that many of the CAPTCHA farms that exist in mostly other countries, the workers there are only paid about $2 a day. So actually, you could get a big raise by answering questions for blind people. But let's do a little bit more math here. So that was the average time, but maybe we could over time train some workers to be able to do this more quickly. We actually found that there were a number of workers who could answer questions for 10 seconds or less. So we follow through with the same, and that's getting a little bit more attractive at $2.40 an hour. And then how you get up to minimum wage is up to you, but minimum wage, federal minimum wage is $7.25, and so you need to essentially triple the wage that we have right now. Even if you tripled the price that you're willing to pay for these workers, you're still able to answer over 6,500 questions for the same price as a very specific access technology costs right now. And so I think thinking about these issues, and my point is not to tell you that we've solved all of this, but especially in this space, I think human computation, even paid human computation, can make sense because of arguments like this. So in the last part of the talk, I'm just going to talk about how we've started thinking more carefully about how we can mix human and artificial intelligence. This is Keanu Reeves in Johnny Mnemonic. Anyone's favorite movie out there? No. So what's kind of neat is that once we have this human computation that's readily available, that works pretty quickly, we actually can build systems that are essentially deployable Wizard of Oz. So Wizard of Oz, the Wizard of Oz technique basically means replacing what you might build eventually with automatically, that would work automatically, with people. And so this has long been used as part of studies that you use to validate that something you might, or you're thinking about building that would take you a long time to implement might be a good thing to do, right? So why spend 2 years of your life building something only to realize that people don't actually want it anyway? And so you might use this to help figure out if it's something that would work or be useful. But now that we can do that, we can actually put the wizard right in people's phones. And one example I'm just going to describe briefly of how we've done that is with this project called VizWiz Locate It, where we've demonstrated how you can prototype these new tools, these new interactions, and kind of actually study them with real people, because now we can do this human computation in nearly real time. So the motivation for this project was that we found many of the identification problems that we saw people ask. So they would ask, is this the can of corn? Is this the can of corn? Things like that. Weren't really because they wanted to know if that particular can was corn, but because they were looking for the can of corn, right? And so we thought we could better support this type of query by combining the human vision, human computer vision, with automatic computer vision. And so instead of asking, is this the can of tomato soup over and over and over again, we might be able to ask just, where is the tomato soup can once? And so I don't have time to go through exactly how all of this works, but I'm just going to go through what it looks like from the user's perspective. So first, the user takes a kind of overview picture of the approximate area where they think what they're looking for is. So in this case, we have a shelf full of different cereals. Then they send the overview picture off to Mechanical Turk, along with the description of what they're looking for, say the Wheaties. The remote worker this time, instead of in the normal VizWiz case where they answered a question, here they just outline what the item that the user asked for. So in this case, the user or the worker has outlined the Wheaties. That gets sent back to the phone where it's used as a computer vision descriptor. And now the hard part of computer vision has been solved, right? Because now we know what we're looking for. And not only that, computer vision is very good at finding the same object from the same perspective in the same lighting conditions again. But it's a lot harder to say, I'm looking for a chair or the Wheaties or whatever else you might be looking for. And so now we can use the automatic computer vision to help the user zero in on the object that they might be looking for. So in this case, the Wheaties. And then just because we wanted to follow this all the way through an example, then they might even be able to use VizWiz again and use the human computation to find out details about that box of Wheaties, like how many calories it might have, things like that. So one of the things that we learned from doing this is that computer vision is hard. But we were able to succeed pretty well just by the fact that we had humans do some of the hardest parts. So we ran a study with just 7 participants where we compared performance in finding a particular box of cereal between 2 different devices. One was the ID Mate 2, which was this commercial product that does barcode scanning, and it speaks the product name. So basically you find an object or an item, and you might have to run the barcode over the object a little bit. But when you find the barcode, it actually will speak the item's name out to you. And our VizWiz Locate It, which works as I just described. So the barcode scanner actually worked all the time. It was actually worked really well. Our project did not work all the time. It worked 12 out of 21 times on the first try. And then we got almost all of them on the second try. But they had similar times, task completion times. And what's interesting about our system as compared to the barcode scanner is that not everything has a barcode on it. And so ours is actually general to any searching task. And what we were able to do is 2 things. One was we were able to find some of the more difficult problems that we'll need to address to make this work really reliably. And then we got a better sense, because people could actually use, with this quickly prototyped system, we got a better sense of whether they thought this was actually valuable, right? Getting back to the problems that we saw, well, we had a higher error rate, similar time, and ours is generalizable. Some of the problems we saw were, and you might not expect, because most of the examples I've shown you are these carefully framed pictures. That's not what blind people take, right? So when they were using our system to find their cereal box, the pictures were more like this, where they were blurry, they were tilted, they were scaled in differently than what we expected, or improperly framed, so they had multiple cereal boxes in the same frame. And so that can be very hard for computer vision to figure out. Even though we had an accurate descriptor of what we were looking for, it can be still hard to figure out what item is in front of you. So what the benefit here is, though, we can actually prototype quickly this new technology and figure out, is this something that we should invest time in building something automatic to do? And then if so, what are the hard problems? We've explored the similar idea in a talking mobile OCR project that we have, where users take a picture and we actually provide them automatic assistance in aligning text. We split the text into different sections so that they can then be sent off to OCR and or human-powered text recognition through the network services. So it's pretty easy for computer vision to split up text. We can even find things like headings, which allow us, if we can recognize those first, we can allow the interface to more more easily support the type of interaction that people want, right? They want to go through the headings first and then maybe drill in deeper, whereas if you just OCR'd everything, then you wouldn't be able to do that. And then, because especially a lot of menus and things like that have kind of strange fonts or script fonts that OCR doesn't handle well, if the user comes across a piece of text that doesn't seem to have been OCR'd correctly, then we can send that off to a human for fixing. And so I have a video here of just the system that is going to help the user align this piece of paper here.
Viewfinder. Image. Tab to focus. Zoom out. Zoom out. Turn left. Turn right. Zoom in. Ready.
So that was the automatic system helping the person align the piece of paper that would then be OCR'd. And what I think is neat about this, and what I'm calling at least hybrid intelligence interfaces, which are interfaces that closely couple the intelligence of the user, the artificial intelligence, and the crowd, is that in that case of Monocle, I think is a good example where you rely on the user to get you close, right? So we weren't trying to detect where the document was across the room. We rely on the user to get close to the document. We use automatic computer vision to help the user just center it right. And then we use computer vision to automatically segment the text and OCR it. And then we rely on the user again to find text that might be appropriate to be sent to human computation. Another concern a lot of people have is, what if Mechanical Turk goes away? And I think that is not a big concern, because there's so many other sources of human work out there. And so one of the things that we're doing right now is we have a version of VizWiz that we call VizWiz Social that allows users to choose between a number of different sources of human computation. Things like online games, Mafia Wars, Farmville, things like that. Social networks, Facebook, Twitter, personal contacts, email, picture text messages. But then the question really becomes, how can users make informed choices? There's a lot of differences between these different sources of human work. And I think we don't know well how to support that yet. So just as a simple little breakdown of things, we kind of know, or we have a way of talking about, reasoning about, and evaluating whether an interface is usable. These are just Nielsen's principles. We also have a way of talking about intelligent user interfaces, whether they are useful, usable, and do what we expect. So things like Eric Horowitz's principles of mixed initiative user interfaces, so where he advises things like intelligent user interfaces should provide significant value, balance the risks of bad predictions with the utility of the help the interface should provide or could provide, and match social expectations, things like that. I don't know if we have a similar set of principles for human computation or interfaces that include humans in the loop in an interactive system. But there's a number of things that are certainly concerns. One is, well, maybe intelligent user interfaces are not always accurate. Human computation has the potential to be inaccurate in different ways. As I'm talking about Mechanical Turk, these strangers are looking at your photos. What are the privacy and anonymity implications of that? If we move to new services like Facebook and Twitter, that might even be worse, right? Because it's not strangers anymore, it's people you know, which might even be worse if they see your photos or your private information. There's differences in latency. So we did a lot of work to try to make Mechanical Turk work quickly, but if we move this to Facebook or Twitter, some of the same strategies we use don't really apply. What does it mean to queue a worker if they're recruited from Facebook, or if they're recruited from your email contacts, things like that? We have to think about the worker interfaces. We saw with VizWiz that if the speech recognition worked, the answers got returned much more quickly. And there's a lot of different new challenges there. So how do you design the worker interfaces such that they preserve things like privacy and anonymity? So they help encourage low latency answers, so that they help encourage accuracy. And then feedback to users. So how do you help users understand if they're sending a question to Facebook versus Mechanical Turk? What are the implications, right? So what are the implications in all of those other dimensions that I mentioned there? So in accuracy and latency, privacy, anonymity, and things like that. So just in conclusion, I talked about human computation, and in particular I talked about nearly real-time human computation that can be used as part of interactive systems, can be used for prototyping new types of tools that can't really exist right now because we don't have the automatic technology, or that automatic technology is error-prone and therefore often not used by people or not used to its fullest potential. I think this builds on how people with disabilities get answers now, right? So in the end, if other strategies fail, if the technology fails, then you might ask a friend. And so this is doing the same thing, but preserving independence, right? So you're actually paying a worker to do this instead of asking a friend. You can build these quickly deployable prototypes to understand more richly what the problems you might run into are if you develop a new type of interface, a new intelligent user interface. And then also you can better understand whether people actually want that, right? They want that tool. And then finally, I think there's a really interesting issues in what we might do if we want to design these hybrid intelligence interfaces, these interfaces that employ human computation in concert with artificial intelligence and the user's intelligence. So that's the end. Thank you very much. It was a great pleasure.